Hello dear students. Today we are going to discuss about power in AC circuits in lesson 4. First we are going to speak about the introduction to power in AC circuit. Introduction to power in AC circuit. In mechanics we have come across the term power, which is the rate of doing work. Here also the same idea, but here we are going to speak about electrical work or electrical energy. So power in an AC circuit is defined as the rate of consumption of electrical energy by a circuit. When you are passing electric current through a component in a circuit with the help of a source of EMF, then the amount of energy consumed by the component for a given duration gives you the measure of power consumed by a circuit. So power in an AC circuit is defined as the rate of consumption of electrical energy by a circuit. Electrical energy by a circuit. And we can say here power of a circuit or power in an electrical circuit is the product of voltage and current. Power in a circuit is the product of voltage and current. For direct current circuits, we can simply take the product of the applied voltage and applied current so that we can obtain power. But in an AC circuit, we cannot do so. Why? The reason is very simple. In an AC circuit, the voltage and the current varies at every instant of time. It varies with respect to time at every instant. So, what we are going to do is, first we are going to calculate the instantaneous power by taking the product of instantaneous voltage and instantaneous current. And then we are going to take an average over one complete cycle so that you will get the average power consumed over one complete cycle. So how will you calculate average power? First thing, you have to calculate the instantaneous power. How will you calculate instantaneous power? If I write this P, I, this is for an understanding I am writing. You can simply represent it as P. Simple. So Pi is the instantaneous power. It is the product of instantaneous voltage and instantaneous current. This small I letter symbol represents the instantaneous voltage. Instantaneous means right at that particular instant, at that particular time. What is the value of voltage and what is the value of current? Then when you take the product of these two, you will be getting the instantaneous power. As you were given explanation for the representation of the notations of instantaneous voltage and instantaneous current, I can write P equals small letter V into small letter I. That's all. Simple. Instead of representing like this, we are going like this. P equals small letter V into small letter I. Small letter V represents instantaneous voltage. Small letter I represents instantaneous current. I am taking the product of these two. What will be the result? Instantaneous power. Then you go for an average over one complete cycle. One complete cycle here refers to time duration from 0 to capital T. So if you integrate the entire power calculated or the instantaneous power calculated between the limits 0 to capital T and you divide it by the total time, then you will get the average. So you are summing up the power consumed by the electrical circuit over one complete cycle by taking integration between the limits 0 to capital T. What will you get? You will be getting the total power consumed between this duration, 0 and capital T. If you divide it by capital T, then you will get the power consumed by a AC circuit, average power consumed by an AC circuit. How will you calculate average? You will be adding up all the values and divide it by the total number. That's what you are doing here. You are taking the average power between the time duration 0 to capital T and you are dividing it by capital T so that you will be getting the average power. So we shall go on with the calculations. Let us say the instantaneous value of voltage is represented as V equals Vm sin omega t. And the instantaneous value of current is represented as I equals Im sin omega t plus phi, where phi is the phase angle. It is the phase difference between the voltage and the current in a AC circuit. So it is the phase difference. Phi is the phase difference between voltage and current in an AC circuit. So V equals Vm sin omega t, I equals Im sin omega t plus phi. So to calculate the average power consumed, we can write, or to calculate the instantaneous power, we are going to take the product of voltage and the current. Voltage is Vm sin omega t. Current is Im sin omega t plus phi. Vm and Im can be taken separately. Sin omega t is there, and then sin A plus B is sin A cos B plus cos A sin B. Right? So this is Vm, Im, sin omega t. I am taking sin omega t into cos phi, or sin omega t inside. So sin omega t into sin omega t becomes sin square omega t into cos phi plus sin omega t cos omega t into sin phi. So this is the instantaneous power. This is the instantaneous power consumed. We have to calculate the average power consumed by the circuit over one complete cycle. So we can write the average power like this. Integral of 0 to capital T, V, small letter v, small letter I, into dt divided by integral 0 to t dt. This is the representation for average power consumed over one complete cycle. So what am I doing here? I am taking the product of instantaneous voltage and instantaneous current, and then I am taking a sum of all these instantaneous values between the limit 0 to capital T for one complete cycle. I just added all the values and I am dividing it by capital T. Then you will get the average. So we can go on with the calculation now. As we saw, the product of V and I is Vm Im sin square omega t cos phi plus sin omega t cos omega t into sin phi. Let me represent the equation in a different form. The average power consumed, P average is equal to integral 0 to t Vm Im sin square omega t cos phi plus sin omega t cos omega t sin phi into dt. This is how the representation must be. Integral 0 to t into dt. Vm and Im are constants. I am taking this out. Vm Im. Integral of dt is small t. When substituting the limits upper limit and lower limit, I will get t minus 0. So simply it will become t. So I can write integral of 0 to capital T into dt as simply t. Actually, how will you write? 0 to capital T, dt is t between the limit 0 to capital T. Upper limit minus of lower limit. T minus 0 is simply t. So I just took t out. That's all. So integral of 0 to capital T dt is capital T itself. Then integral 0 to t can write sin square omega t cos phi into dt. I am separating this as two integrations. Plus integral 0 to t sin omega t cos omega t sin phi into dt. And we can say the value of cos phi is taken out. Integral of sin square omega t into dt is simply the average over one complete cycle is half. This quantity will become half. And the average of sin omega t cos omega t into dt is 0. We can just have a proof for that. Vm Im divided by t into these two integrations, sum of these two integrations. I would like to solve these two integrations one by one. I am taking this first integration and then this one is the second. Integral of 0 to t. Cos phi is constant. I am just taking it out. See, I am doing the calculation for these integrations. I am just holding this expression up to this in order to explain that integral of sin square omega t into dt over one complete cycle is equal to half, and integral of sin omega t cos omega t dt over one complete cycle is equal to 0. I am checking out the integration. I am showing you the integration. Cos phi is taken out, a constant. Integral 0 to t sin square omega t into dt. So this first expression is cos of phi. Sin square omega t can be taken as 0 to t 1 minus of cos 2 omega t divided by 2 into dt. Sin square omega t is 1 minus of cos 2 omega t divided by 2 into dt. So cos of phi is taken out 2 is there, which is taken out. I can write integral of 0 to t, dt is taken. So integral of 0 to t dt minus of integral of 0 to t cos 2 omega t into dt. Cos 2 omega t into dt. Then this is for this cos phi by 2 is constant for these two integrations. So once again, cos phi divided by 2, it is kept as it is. Integral of dt is t. It is between the limit 0 to capital T minus of integral of cos 2 omega t dt is sin 2 omega t divided by 2 between the limit 0 to capital T. Sin 2 omega t divided by 2 between the limit 0 to capital T. Now, cos phi by 2 is there. If you substitute the upper limit and lower limit for the small t, I will have t minus of 0 minus sin 2 omega t divided by 2 between the limit 0 to capital T. As we know, t is equal to 2 pi by omega. I am going to substitute for small t as capital T, which is equal to 2 pi by omega. So this expression will be sin 2 omega, I am taking 1 by 2 out first. Sin 2 omega into small t is replaced as capital T minus of sin 2 omega into 0. This is how the expression will come. So this is cos of phi divided by 2 t minus of 0 minus of half into sin 2 omega instead of t I can write 2 pi divided by omega minus of sin 0 is 0. Omega gets cancels out. Sin 4 pi is also 0. So the entire term becomes 0. Then what will be the result here? It is simply cos phi by 2 into t. Cos phi by 2 into t. So for this entire integration, cos phi is constant. When you take this out, then integral 0 to t sin square omega t into dt will be simply equal to t by 2. Or I can say for the average value over one complete cycle, for this particular integration sin square omega t dt is equal to simply half. That is what I am obtaining here. See, you just look at the integration here. I am just taking the constant out, I am solving it, and I am getting a value cos phi by 2 into t. As cos phi is constant, it is already taken out, and t is there. If t gets cancels out, you will get a half. So simply the value of this particular integration is, I can say, cos phi into t by 2. Let me keep it as it is. Cos phi into t by 2. Then, for the second integration, I am just rubbing it. For the second integration, the value, I told you the value is 0. As you know, sin 2 theta or sin 2a equals to sin a cos a. So sin a cos a will be equal to sin 2a divided by 2. So I am going to write sin 2a by 2 instead of sin omega t cos omega t. So that integration gets transformed to 0 to t sin omega t cos omega t, sin a cos a. That's the form where the expression is existing. So I can write sin 2 omega t divided by 2 into sin phi into dt. Sin phi is constant, so I can take out. Sin phi is constant, 2 is constant, which is taken out. Integral 0 to t sin 2 omega t into dt. This is the expression, sin 2 omega t into dt. What is integral sin theta? It is minus cos theta. This is sin of nx, integral of sin of nx. So minus cos nx divided by n. That's the form. So sin of nx is minus of cos nx by n. So I can write this integration in this form. Sin phi divided by 2. Integral of sin 2 omega t is minus of cos 2 omega t divided by 2 omega. Between the limits 0 to capital T. Take this 2 omega out. So for simplification, I can write sin phi divided by 2 into 2, 4 omega. Minus is there, so I can take the minus sign out. Then cos 2 omega, instead of small t, I am substituting upper limit capital T, minus of cos 2 omega into 0. So minus sign is there, sin phi is there, 4 omega is there, cos 2 omega into t. As I mentioned earlier, capital T equals 2 pi by omega. So cos 2 omega into 2 pi divided by omega, minus of this entire argument of cos is 0. Argument in here refers to the value which is coming after the sine or cosine functions, trigonometric functions. So this is called argument. This is called argument. 2 omega into 0. So this entire term is 0. Cos 0 is 1. So simply I can take this as 1. Omega gets cancelled out. Cos of 4 pi. Cos of 4 pi is also 1. Cos of 4 pi is also 1. What is 1 minus 1? 0. So the entire term becomes 0. Product of this value will also give you 0. That is why I told you the integration over one complete cycle, or when you take integration of the sin omega t cos omega t over one complete cycle, the result will be equal to 0. So this integration gives you a value 0, and this entire integration gives you a result cos phi into t divided by 2. Let me proceed further now. So we just had an idea how integral of sin square omega t dt is giving you half for one complete cycle, and the integral of sin omega t cos omega t into dt equals 0 for one complete cycle. Right. Now I can write the result of this integration, which is Vm Im by capital T into cos phi into t divided by 2. T gets cancelled out. Vm Im by 2 cos phi. This is the average power, P average. And this can also be expressed as P average is equal to Vm by 2 or Vm by root 2, Im by root 2 into cos phi. See, root 2 into root 2 is 2. So 2 is splitted out. What is Vm by root 2? Vrms. What is Im by root 2? Irms into cos phi. So P average is equal to Vrms, Irms, cos phi. Or P average equals Vm by root 2, Im by root 2, cos phi. Or P average equals Vm, Im by 2, cos phi. These are the three different ways by which we can express the average power consumed over one complete cycle by an electrical circuit. Here, this average power, P average, is also called true power. This Vrms, Irms is called apparent power. Apparent power. Cos phi, this term is called power factor. Cos phi is called power factor. So P average is called, average power is otherwise called true power. Vrms, Irms, the product of RMS value of voltage and RMS value of current is called apparent power. And cos phi, power factor, we can say here. What is this true power? We can simply say this much amount of voltage, RMS voltage, virtual voltage, and this much amount of virtual current is flowing through a AC circuit, where the component consumes this much amount of power, average power. Because Vrms, Irms is coming as a product with cos phi. Depending upon the value of phase angle phi, between current and voltage, this cos phi term, power factor term, will be varying. With the varying values of cos phi, this product will also change. Vrms, Irms will also change. Which means, depending upon the value of the phase angle between the voltage and the current, the average power consumed by an electrical circuit varies. So, the amount of power that has been consumed by the circuit, which is used by the circuit, which is dissipated as energy, is termed true power of the circuit. Then what is apparent power? Apparent power is the sum of true power and the wattless power. We can say wattless power. We are going to discuss about that. So, if 100 rupees is given to you, 50 rupees is spent in a useful way, and the remaining 50% or 50 rupees is not at all used by you. It is left as a loss. It went as a loss. Then we can say the 100 rupees here is termed the apparent power. The amount what you have spent as a useful one is termed true power, and the one which we have lost is termed wattless power. And we can say cos phi is the power factor, that is different. So we should have a clear picture about this. What is true power? The amount of energy that has been consumed in a given duration, which is spent usefully by a component or by an electrical circuit, is called true power. And the amount of power that has been provided through the circuit, total power provided to the circuit, we can put it in that way, is called apparent power, which is wattful as well as wattless. It is the sum of wattful power and wattless power, apparent power, which is represented as Vrms and Irms. Cos pi is the power factor. We shall speak about the special cases related to this average power. What will be the average power consumed in a resistive circuit, in an inductive capacitive circuit, as well as in a series RLC circuit, in a series resonance circuit. We shall check out one by one. We shall speak about the special cases now. If the circuit is a pure resistive circuit, what is the average power consumed? You have seen the phase angle phi between current and voltage is 0 in a pure resistive circuit. The value of power factor cos phi is equal to 1. So average power consumed is P average equals Irms cos phi, which is Irms, or I can say Vrms Irms. So the average power consumed is equal to the apparent power, or true power is equal to apparent power. So in a pure resistive circuit, what is the amount of power provided to the resistive circuit? The total power is consumed by the circuit. See this one? I am giving you 100 rupees, you are utilizing all the 100 rupees. That's the meaning. So the total power provided, the apparent power is Vrms Irms. Average power consumed by a pure resistive circuit is equal to Vrms Irms. Also, we can write Vrms Irms by 2, or I can write, Vm Im by 2, or as Vm by root 2, Im by root 2. These are all the representations which we use to calculate average power consumed by a pure resistive circuit. Now, if it is a inductive or capacitive circuit, what will be the case? A capacitive circuit. As we know, the phase angle between inductive and capacitive circuits, or phase angle between the current and voltage in inductive or capacitive circuit, is plus or minus pi by 2. Cos of plus or minus pi by 2 is 0. So what is the average power consumed? 0. So the average power consumed by the inductive or capacitive circuit is equal to 0. What happens exactly here? We can say, if you consider a sinusoidal wave which represents the power, then the power consumed in 1/4 cycle by the component will be given back to the source in the next quarter cycle. So you are getting the energy and then you are sending the energy back to the source itself. I am giving you 100 rupees, you are getting it, but you are returning it back to me once again. So what is the amount utilized by you? Nothing, 0. That is the way. So the power consumed by the circuit here is 0, because the energy consumed or power consumed in 1/4 cycle is once again provided back to the source itself in the next quarter cycle. So average power consumed is 0 in a pure inductive and a capacitive circuit. If suppose we are going for a RLC series circuit, R, L and then C. If you go for a series RLC circuit, then what is the phase angle here? Phi equals tan inverse of XL minus of XE divided by R. You might have seen this in a series RLC circuit. Phase angle phi equals tan inverse of XL minus of XE divided by R. So power factor is cos of this phi. So we can write simply the average power must be Vrms Irms cos phi. Vrms Irms cos phi. What does this mean? You have to calculate the phase angle here for the series RLC circuit. by knowing the values of inductive reactance, capacitive reactance and resistance. After finding out the value of phi, you have to substitute here so that cos phi will be resulting you some other value. So you can calculate the average value of power consumed by the series RLC circuit. Now, if it is a series resonance circuit, RLC circuit is a series resonance circuit, you might have discussed in the previous sessions that in a series RLC resonance circuit, you can say the RLC circuit behaves like a pure resistive circuit. RLC circuit behaves like a pure resistive circuit. In a pure resistive circuit, what is the average power consumed? VRMS, IRMS. Same is that for a series resonance RLC circuit. So, in a series RLC circuit which is said to have resonance, we can say the average power consumed is equal to VRMS, IRMS, since it behaves as pure resistive circuit. It behaves as a pure resistive circuit. So in a series RLC circuit at resonance, the average power consumed is equal to VRMS, IRMS. So depending upon the values of power factors, the average power consumed by the different circuit elements connected across the alternating sources is different. So in a series, in a pure resistive circuit, average power consumed is VRMS, IRMS. In a pure inductive and capacitive circuit, average power consumed is 0. In a series RLC circuit, average power consumed is VRMS, IRMS, cos phi, where phi is the phase angle between voltage and current. And in a series RLC circuit at resonance, the average power consumed is VRMS, IRMS. The series RLC circuit at resonance behaves like a pure resistive circuit. That's why you are getting the same expression. We shall now discuss about wattless current. In an AC circuit, the voltage VRMS is making a phase angle of phi with the current IRMS, which can be represented by a phasor diagram. That this is the x-axis where the RMS current is mentioned, and the RMS voltage is mentioned along this particular direction, which is said to be making an angle of phi with respect to the RMS current, where phi is the phase angle. Phi is the phase angle. As I have represented the voltage in the positive direction, I can say the voltage leads the current by a phase angle of phi. The voltage leads the current by a phase angle of phi. I can say the voltage leads the current by a phase angle of phi. Now we are going to speak about wattless current. In order to have a clear picture about wattless current, first what you are asked to do is resolve this RMS value of current into two rectangular components. Resolve this RMS value of current into two rectangular components. So I can show it like this. The RMS value of current is IRMS. The value of voltage is VRMS. I can resolve this into two components. This is phase angle phi. This is IRMS cos phi. And this one is IRMS sin phi. Now we can say here this VRMS and IRMS cos phi quantity are acting along the same direction. IRMS sin phi is acting perpendicular to the RMS voltage. Now, you can have a simple idea here. While speaking about work done, we might have discussed F force F is said to be acting by making some angle theta with the displacement ds. F vector is acting along one direction, displacement is acting along some other direction. The angle between the two is theta, and the amount of work done can be calculated as F ds cos theta. And we can say here, if the force is resolved into two components, I can write F cos theta and this one is F sin theta. So I have to take a product of F cos theta into ds. To calculate the amount of work done. So if this component acts along this direction, then that will do a useful work. If it is acting perpendicular to this displacement, the force does not do any work. In the same way, I can conclude the component which is acting along the direction of RMS voltage does the useful work, which means it is used as a useful power. The component which is connected across the AC source will be using this much amount of power. So this is consuming this energy from the circuit, from the source, and it is converted into useful work. What about this IRMS sin phi? As it is said to be acting perpendicular to the RMS voltage, it does no useful work. So how can we say this? This RMS cos phi, IRMS cos phi is called active component. IRMS cos phi is called active component. And this IRMS sin phi is called reactive component. Reactive component. So what happens exactly here? In this particular case, this active component IRMS cos phi is responsible for the conversion of the energy obtained from the source into useful work. So we can say a work is done by the component by consuming energy from the source with the help of IRMS cos phi term component. So this is called the active component. And the power consumed, average power consumed, can be represented as VRMS, IRMS cos phi. We are getting the expression once again. P average for average value of power consumed. VRMS, IRMS cos phi. So this power is called wattful power. Wattful power. Wattful power, or in other words, the current which is responsible for this useful power is called wattful current. Wattful current. Power is wattful power and the current is wattful current. This is wattful power and this one is wattful current. This wattful power or wattful current is generally represented with the letter symbol P, and it is represented with the unit watt. That is simple. It is represented with the unit watt. Whereas this reactive component, as I am speaking about IRMS sin phi, this IRMS sin phi is acting perpendicular to the RMS voltage, which does no useful work. See the term? Which does no useful work because it is acting perpendicular. So the angle phi is equal to 90 degree, or the angle between the RMS value of voltage and this component is 90 degree. When you substitute this 90 degree in the angle, then you will get, as we are speaking about work done, W equals Fs cos of theta. The angle theta is 90, cos 90 is 0. So work done is 0. So in this way, this RMS of sin phi, IRMS sin phi and VRMS are at an angle of 90 degree. So the average power consumed by the circuit is said to be 0 due to this current. So average power consumed is 0. What does this mean? It is consuming energy and then it is releasing energy once again to the source itself. So this current does no useful work in the circuit. As it is doing no work, we used to call this as the reactive component. This component is called reactive component and the power is called wattless power. Wattless power, and the current responsible for this is termed wattless current. Wattless current. So this is wattful power or wattful current. This one is wattless power or wattless current, which means this component of current does no useful work in the circuit. Which means if you are providing certain amount of energy, 100% of energy, 50% of or 60% of energy, it all depends upon the value of the phase angle phi. So this much amount of energy is consumed by the circuit and is converted into useful work. Remaining amount of energy is meant as a waste here in this particular circuit, and that waste amount of energy spent by the component, by this component IRMS sin phi is termed reactive component, and it does no useful work, so no useful energy is obtained. So we used to call this as wattless power, and the current responsible for that is called wattless current. This is generally represented by letter symbol Q. Q stands for reactive component IRMS sin phi. Q is the wattless power. Q is the wattless power. Its unit is volt ampere reactive, VAR, which will be represented in terms of capital letters. So VAR, V for volt, A for ampere, R for reactive. So the wattless current is generally expressed with a unit volt, ampere, reactive. And we can say here, any circuit in which the average power consumed over one complete cycle is 0 is called wattless current. Right? Any circuit in which the average power consumed is said to be equal to 0 over one complete cycle is called wattless current. And this happens in the inductive and capacitive circuits. This happens in inductive and capacitive circuits. Generally in inductive and capacitive circuits, because in inductive and capacitive circuits the phase angle phi is equal to pi by 2 between RMS voltage and RMS current. So generally the average power consumed in such circuits is said to be 0. As I told you, in 1/4 cycle the energy will be obtained by the inductive and the capacitive components, and in the other quarter cycle the same amount of energy will be given back to the source. So what is the amount of energy used here? What is the amount of power that has been spent? Nothing, 0. So the wattless power or wattless current will be existing mainly in inductive and capacitive circuits. This is the idea related to wattless currents. The power factor has to be discussed here. Power factor can be generally represented in the following ways. Actually, power factor is cos phi. Power factor is cos phi. So, power factor is the ratio of true power to apparent power. So, this is one way of expressing power factor. Cos phi is equal to true power divided by average power. True power divided by average power, or otherwise P average divided by VRMS, IRMS. What is the unit of power factor? No unit. Why? Because cos of phi is a mere number. Is a mere number. Number has no unit. So cos phi, power factor, has no unit, which is the ratio of true power to average power. Apparent power. True power to apparent power. Cos phi is the ratio of true power to apparent power. Also, the cos phi power factor can be represented as the ratio of resistance to impedance, impedance in an electrical circuit, which is R divided by Z. Resistance has the unit ohm, impedance also has got the unit ohm. So power factor can be expressed in these forms: true power by apparent power, or average power by VRMS, or we can say resistance divided by impedance. Also we can write cos phi as the true power VI cos phi divided by apparent power VI. If we cancel this, you will get cos phi. So this is also the other representation in words in terms of expressions. VA cos phi divided by V. Cos phi is equal to VA cos phi divided by VA. Cos phi, power factor plays the key role in describing about the power consumed by the electrical circuits. Now, we shall speak about the power factor in various circuit elements. Let us say, in a resistive circuit, phase angle phi is 0 between current and voltage. So cos phi will be equal to 1, because cos 0 is equal to 1. So the power factor in a pure resistive circuit is equal to 1. What does this mean? What does this explain? If cos phi is equal to 1, I can say cos phi is also equal to true power divided by apparent power. So true power equals apparent power. What is the average power consumed by the electrical circuit? That is equal to the average power, or that is equal to the power provided by the circuit. Power given, power taken, both are equal. That happens in a pure resistive circuit, because cos phi, power factor, determines that cos phi is equal to 1. And then in an inductive or capacitive circuit, in LRC, in an inductive or capacitive circuit, phi equals pi by 2, plus or minus of pi by 2, between current and voltage, cos 90, cos plus or minus pi by 2 is 0, so we can say power factor is 0. Cos phi, power factor is 0. So power factor here is 0. What does this mean? True power is equal to 0, or average power consumed is equal to 0, which means power is obtained by the component in one quarter cycle and is returned back to the source in the next quarter cycle. So no energy is used by the component to do useful work. That is the meaning. So in an inductive or capacitive circuit, cos phi is equal to 0. In a RLC series circuit, as we can say, cos phi is equal to P average divided by ERMS IRMS. P average divided by ERMS IRMS. The value of power factor in a pure RLC circuit ranges between 0 and 1. The maximum value of the quotient value is 1. So we can say the power factor has a maximum value 1. And the minimum value, or the minimum value is 0 here in this case. Minimum value is 0. So the value of the power factor in a series RLC circuit ranges between 0 and 1. 0 and 1. So in a pure resistive circuit, the value of power factor is 1. In an inductor or capacitor circuit, the value of power factor is 0. And in an RLC series circuit, the value of power factor ranges between 0 and 1, depending upon the values of average power and apparent power. So the value varies. So what do we say here? If power factor is obtained as 0.5, then we can say the average power, I am just doing it as an example. If power factor cos phi is 0.5, then 1 by 2 equals average power divided by ERMS IRMS. So average power or true power is equal to half of ERMS IRMS. What does this mean? The power provided by the source is ERMS IRMS, and of that power, half of the power is utilized as true power or useful power by the circuit, which is expressed as P average equals half of ERMS IRMS. That's the meaning. So it all depends upon the value of power factor. Power factor decides the amount of power consumed by the circuits, right? That's all about the power factor.